Hi, welcome to this webinar. My name is Vivek Singhal. I am a co-founder and chief data scientist with Selftrack. We are an AI startup based in Bengaluru, India, with branch in New Delhi and a global research lab organization. Today I'll present an advanced webinar on GANs or generative modeling GANs. GANs are generative adversarial networks, okay, specialized neural networks for used in generative modeling. Okay, let's begin here. So just a plug on our startup Selftrack. We are an AI startup based in Bengaluru and New Delhi. Uh, we are into AI training, AI consulting, and AI research. So we run a Selftrack AI lab with the local chapters in Bengaluru and Delhi, and as well as a global membership profile. Okay, so we have almost 55 members as of today, and this number is growing rapidly. So we are working on cutting edge AI algorithms in machine learning and deep learning, and our objective is to disrupt many industries with help of advanced artificial intelligence. Okay, let me just change the pen color here. I always like blue better. Yes. Okay, and we are working on multiple machine learning innovations, and we produce a lot of content and webinars in this space. Some of it you'll find on our public YouTube channel. Okay, and for our lab members, we have advanced webinars on our private YouTube channel. All right, let's continue here. So this is me, your presenter today. Um, I was based in the US for 16 years. I worked for companies like AT&T and Schlumberger, and then I came back to India in 2012, worked with IBM for 2 years, and since 2014, I've been involved in multiple startups such as Healthyfly and Walkwell. This Selfstrat is my latest AI startup, and we do some cutting edge research in AI, as well as we are working on producing multiple proof of concept products in this space. Okay, and I personally specialize in machine learning and deep learning technology. We are working on multiple POCs related to computer vision, NLP, time series, etc. Some of our research content you'll find on our research blog. You can check it out. And we have produced training and research content for multiple corporate customers as well. Okay. I'm also the AI training advisor for Simply Learn and Manipal Education Group, and I made their machine learning and deep learning courses. Okay. So now we provide our own courses. In case you have interest in learning machine learning, deep learning, or advanced AI internship, reach out to us offline. Okay. Let me continue here. So let's discuss generative adversarial networks. So these are neural networks trained on large amount of data. Okay. I mean, they are still unsupervised learning, but I do need some real images to train them to produce artificial images which look like real images. The idea of GANs is to produce output that contains new data similar to training data. They do so by learning the natural features of the training dataset. A gradual learning enables this network to produce output which looks similar to training data. Basically, GANs produce fake data which looks like real in very simple terms. So they learn to produce data which looks as good as real. So GANs do represent unsupervised learning, and there does not exist an explicit desired output. Okay, so it's not X and Y combination like sorry, like in neural networks regression or classification. Okay, so while there is some data available, but there is no corresponding output Y label. Okay, so it is unsupervised learning technically. For example, you can take millions of real images, and GANs can learn to produce images similar to training data. In other words, realistic images. The advantage of GANs is the neural network is learning how the real world looks like, Images so produced by GANs could be sharper than the training images. So in some cases, I could produce images better than the training images. Okay. So if I was training my model on Picasso or Michelangelo art, I could produce perhaps even better art theoretically. Okay. New kinds of art patterns can be produced. So it is generative modeling. It's able to produce n number of generative content, whether it be art, images, music, etc. Okay. Okay. So, GANs were invented by Dr. Ian Goodfellow, a professor at University of Montreal, and his PhD guide, Dr. Joshua Benjo at the same university, and another professor called Aaron Corwell, same university, University of Montreal. And the paper which they wrote on this is shown here. Last year, MIT Technology Review magazine rated GANs as one of the most impactful technologies for last year for 2018, and they profiled Dr. Goodfellow as GAN father. Okay, GAN father because he invented GANs. Okay, but technically he invented it with help of his PhD guide, Dr. Benjo, and his associate professor, Aaron Corwell. All right, let's continue. So there's a signature book in deep learning by Ian Goodfellow called Deep Learning. So that is the signature book in deep learning. It's pretty hard to understand, so not recommended for beginners. Okay, let's continue here. So how do GANs really train? That's the question. So the assumption here is if you are seeing this video, then you are expert in artificial neural networks. Okay. If you are not, then I would recommend that first you see some sessions on basic neural networks and convolutional neural networks before coming to this session. So this is an advanced neural network which comes after basic CNN and ANN, okay, and RNN. So the assumption is you already understand your artificial neural networks and convolutional neural networks. So how do GANs work? Basically, there are two neural networks. Okay. Basically, there are two neural networks. So they are fighting with each other. So we call them dueling, as in the English word duel, right? Duel means a fight, correct? Duel means a fight. So these are two dueling networks, which is producing fake images, and this is the judge, this is the criminal, this is the judge. So the judge is saying that what you are giving me is fake, and the judge is comparing the fake images with real images. Okay. So the discriminator, the criminal, is producing fake images. The judge, sorry, the generator of the criminal is producing fake images, and the judge or the discriminator is trying to distinguish fake from real. And then judge tells the criminal, hold on, the image you sent me is fake. Okay, this is not real. So this loop continues. We do combined loss minimization of both the neural networks. Eventually, the generator, the criminal, wins, and it is able to produce nearly real-like images. Okay. Ultimately, these fake images start looking like real images. The judge or the discriminator actually loses this game. Okay. Normally, the good guy has to win. In this case, the good guy loses. Okay. The bad guy, the criminal, the generator wins and is able to create forgeries which look like real. Okay. So this story has a bad ending where the criminal wins. Well, technically, in terms of movie like sense, it's a bad ending, but in reality, it helps us because using this technology, I can produce new fashion design, new shoe design, new bags, new interior design, new building design. I can produce new music, new videos. In future, I will not need Hollywood and Bollywood producers technically, theoretically. I could produce movies with this. All right. So this is incredible technology. So here we are saying that one can feed 200 generated images and 200 real images into the discriminator. This is the judge. Okay, this is a judge, and train them to classify as real images or generated images. So discriminator is trying to distinguish generated or fake images from real images, and the generator is producing images and trying to make them real, right? So we have to always think in terms of two neural networks here: generator, discriminator, to avoid any confusion. Generator is the criminal, okay? Discriminator is the judge. The criminal is the forger. He's trying to give forgeries to the judge. The judge has to tell the generator, hold on, you are giving me forgeries, not real. I have seen the real ones. What you are giving me are not real. In this continuous loop process, combined loss minimization, the generator or the criminal figures out how to fool the judge and produce real images instead of fake images. Okay, the judge actually loses here. The discriminator loses. So the generator G is trying to fool the discriminator D by generating fake images which are close to real images. Discriminator is always trying to distinguish them. So it is a zero-sum game. Okay, both parties are not winning. One has to lose for the other to win. So it's a battle, it's a duel, it's a fight. Okay, so who is up for a fight here? The training procedure for G is to maximize the probability of D making a mistake. Okay, so the criminal wants the judge to make a mistake. In the end, the generator is outputting images that are indistinguishable from real images. Okay, right? I hope this is clear. We'll see a bit more on this shortly. Generator generates synthetic images. Yes, that is correct. Generator creates synthetic or fake images, and it tries to produce real like images so that the discriminator is unable to distinguish them from real images. That is the whole logic. The logic is actually very simple. It's a judge and a criminal. The criminal is trying to produce forgeries, and the judge is saying, hold on, this is a forgery, it's not real. Eventually, the criminal wins and is able to produce real like images. Okay, and this could apply to any other kind of content like music, video, audio, anything, text. Okay, let's continue here. So this diagram explains it nicely. So initially, when we start the training process, the generator takes some random noise and tries to produce images. IMG is image. The discriminator is getting real images also as a feed. So the discriminator tries to compare this with output label 0, and it tries to compare the real images with output label 1. Okay, and there's a reverse feedback loop. Discriminator tells the generator, you send me a 0. The generator initially is producing zeros, fake, right? But the generator is trying to go from producing fake images to real images, 1. Okay, so initially this is 0, this is 1 because that's fake. But the generator is trying to convert the fake into real. The discriminator just told it, well, what you send me is fake. Generator tries again, tries again, tries again. This loop continues till the generator starts producing 1, which means real images. Okay. Eventually, the discriminator gets 1 here and 1 here. And at this point, the discriminator is unable to distinguish that what came here were not real. They look like real only. So it marks them as output as 1 and this also as 1. So at this point, the generator, the criminal has won. Discriminator, the judge has lost. Okay. Let's continue here. You'll notice some very key aspects here. So you must, assuming you know your artificial neural networks and the concept of loss minimization in a neural network, here I am doing one singular loss minimization, correct? Whereas here I am doing two different loss minimization. One loss is for these images, the generated fake images. One loss is for the real images. Okay. So generator runs one time. For every loss minimization iteration of generator, the discriminator has to minimize two losses. Okay. Here, whatever comes here, generator tries to compare this with output label 1. Whatever comes here, The discriminator tries to compare this output. There was 1, 0, and this one with 1, right? So 0 means fraud, 1 means truth, real. Okay. So, okay, let's continue here. I hope this is clear. Let me go on to next slide. Okay, there's a question here. Can the cycle continue even after judge is unable to distinguish the fake image? This way, the fake image can be even better than genuine images. So can the cycle continue even after judge is unable to distinguish fake image? Yes. So as we said, in some cases, our generator here learns to produce even more sophisticated content than the original content. So it need not be precise. It will be mostly a variation of the real image, right? So for example, generating house designs. So our generator might learn to produce more creative house designs than the actual real images which persist. Okay, so it will stop. The discriminator and the generator training will stop at the point when the discriminator no longer is able to distinguish fake from real. But by that time, it's possible that the generated fake images are even more superior in quality to the real images. It is possible, yes, because they are actually slight variations of the real images, right? Like more beautiful house designs, okay, or more beautiful celebrity faces, if you will, right? So that way it could technically produce even better. So it's an artist. The generator is an artist. Generator could learn to produce super fine art, which is even better than current art. Okay. Generator here is an artist. He is a forger. Forger is a criminal who creates duplicate of art or other content, right? That's what is a forger. So this generator is a forger. He's an artist, but he's a forger. He's a criminal. Let's continue here. So we will show a code demo in this session today, where we will show how to train a GAN model to generate MNIST handwritten digits. If you are familiar with MNIST, you might have encountered in classic machine learning or deep learning solutions. So MNIST is a data set of 70,000 images having handwritten numerical digits from 0 to 9, right? And there is a label attached to it, a digital label which marks this image as 0 and this is 9. So of course there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 such images, right? There are 10 possible images with containing 10 possible numbers. So there is an X information, which is the image, right? And there's a Y information, which is the digital label, what this image contains, all right? So we will train a model here, which will learn how to produce MNIST images, all right? We'll show that shortly. Let's continue for now. So here you can see, this is basically discussing what we described. So random noise is coming. Initially, it's random noise. Later on, there's a reverse feedback loop. So the forger, the criminal, is trying to create forgeries. The discriminator, which is the judge, is marking which one is a forgery, which one is real. Okay, and then for the forgery, the discriminator is sending a signal back to the generator. You send me a forgery. Eventually, the generator starts producing real images, and the discriminator fails to distinguish the generated image from the real existing image. Okay, so that's what it is. So here the discriminator for false tries to output a 0. For real, the discriminator tries to output a 1. Okay, and this guy initially is only able to produce 0, but eventually the generator starts producing 1. So then this also becomes 1. The discriminator fails. So this is just a repetition of what I described before. Let me continue. So few more points here. So goal is to maximize dy for reals and minimize for fake. Basically, the The dy is the, so y is coming here, right? This is y. So, and this is z, right? So the idea is that discriminator runs on y, the fake images, and is trying to, maximize the probability that this is real and this one is, and maximize the probability this one is fake, right? G and D play a opposing or dual role, hence the term adversarial training. Adversary, the word adversary means, enemies, right? That's what an adversary means in English. So that's why we call them generative adversarial networks. There are always two neural networks involved here. We train a G and D in alternating manner. Each network gets optimized here. So pretty much it's regular artificial neural network training. No difference. The generative model gets better at producing real-life images, and discriminator gets better at detecting fake. The discriminator gets more and more. The judge becomes also more sophisticated and is able to detect forgeries. But eventually the generator wins and the discriminator fails. The judge actually eventually fails after a while. Okay. So in the end, generator will produce images which are very close to real images. Okay. Now let's see the loss minimization, how it looks like. Okay. So if you see, there are two losses involved. One is the generator loss. The other is discriminator loss, right? The discriminator loss, there are two neural networks. So correspondingly, there are two loss functions. So the generator loss is initially high, the green line, but eventually it stabilizes, right? The discriminator loss is low, eventually it stabilizes. So basically both the loss functions reach an equilibrium point. Okay, they reach a equilibrium point, but this can take a lot of training iterations. Okay, and when they reach the equilibrium point, we have a generator which is producing near real life images. Okay, let's continue here. The question: can we specify any hyperparameter to stop the loop if the generator produces consecutive and real images? Otherwise, if the loop stops on the very instance of fake getting predicted as a real, this could be a chance that the discriminator wrongly predicted. Well, that's just how you code it, right? So, do you do early stopping and you say, well, I need 5 images to pass? So that's, we'll see the code and we'll see how that could be configured. So that's really programming logic, how you will stop the training to finish. Okay. So at some point you may say, well, it's enough and nearly real image is good enough. So those are just, you're right, it's kind of a hyperparameter decision, the way you code it. Okay. What is the metric of success? If both the losses are minimized. Actually, if you think about it, to expand on this point, you see there are two loss minimizations going on. You know your gradient descent, I hope. So there are two loss minimizations going on. This is the discriminator loss. This is the generator loss, right? So ideal weights here are found here. Ideal weights are found here, right? Theta is the weight on the x-axis. On the y-axis, we have the loss function. So, I mean, it will stop here, right? That's when a neural network stops training, when it reaches the zero gradient, and it will stop here, right? So when both of them reach 0 point, the training will stop basically. Whatever has happened by that time, it has happened. If you want to do early stopping, and you might say, well, I don't have to reach 0 point on the loss function curve. I will stop little bit above that, right? So you could stop a little bit above that, not at loss. So this is called early stopping mechanism, so that the model does not keep training forever. In neural network training, what can happen? Sometimes uncontrolled, unstopped neural networks can go on training for a long time. They can also overfit. To regularize, we do early stopping. Okay. What are the internal structure of generated discriminator? Yeah, so I could use both fully connected neural network or CNN. Both kind of neural networks can be used here. Okay. Particularly, I'm talking in context of images. If I'm doing images, I could use both fully connected and CNN. CNNs will have better accuracy because they are specialist in image processing. If I was dealing with text generation or a audio file generation, right? Then possibly, theoretically, we can use RNNs, I suppose. I haven't seen use of RNN in GAN, but I'm thinking why not? If I'm dealing with an audio file or a text stream as the content output, then I could use RNNs in both the neural networks theoretically. I haven't seen that example, but I'm just postulating it here. Okay. But typically we see CNN and ANN all the time in GANs. And CNNs tend to do better for images particularly, as you know. Let's continue. So this is showing something what we call a stacked GAN. So sometimes you stack a GAN over another GAN. Okay. The idea is to improve on the previous results. Okay. So here you see stage 1 GAN, stage 2 GAN. Stage 1 GAN has been trained to produce these images based on just a text line. Okay. So I'm using a text line to produce stage 1 images, and then in stage 2 of the stack GAN I am improving on those images by applying one more GAN layer. Okay, so one more GAN network. So there are two GANs operational here, stage 1 GAN, stage 2 GAN. The stage 2 GAN is producing slightly more accurate but high resolution images. So it may be difficult to make out on the slide, but stage 2 GANs are producing more clear images in general. Okay, stage 1 produces low resolution image based on text statement. Okay, right, and stage 2 GAN produces more sharper images based on results of stage 1 and also the text statement. Okay, so the stage 2 GAN is using both the stage 1 output and the text statement to produce even more sharper, higher resolution pictures, which represent that caption, textual caption. So the images represent the textual caption. So basically, this is incredible technology if you think about it. I could write I could write a story in words, and my GAN stack GAN architecture will produce the same story automatically in images, right? Isn't that wonderful? So I can just write a story in words. I can start writing a story. I went to the market. I saw some interesting products to buy, but really I wanted to buy only the grocery. So I'm writing a story. I am an author. Based on my story, the stack GAN will produce images out around it, around that story. So an image based story will be produced based on my textual story. So this is incredible technology. In future there will be movie writers writing you know novels or just the movie scripts, and automatically I'll be producing motion pictures just by reading the creative script of the movie writer. Okay, so you can imagine the technological capabilities. I mean, if you think about it, I mean, I don't know how the world will look like in a couple of years. The the power of this artificial intelligence is, it's like incredible. It's just thrilling. Yes, it will impact a lot of jobs. What will all those content producers, movie producers, authors do? That will be the question. Okay. Anyway, I'll leave that there. But so far, it's not accurate to replace all those jobs. But we, the data science community, are trying to get there, as you know. Okay. So here we are showing the MNIST image generator. Okay, so I am able to. So there are 9 boxes here, even though they look like merged. So there is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm outputting the output of an MNIST digit generator. Okay, after set of epochs. So I'm doing it 6 times. So it is, as you can see, it starts with producing random noise, then starts going towards the digit, starts producing more and more handwritten accurate digits. Okay. Let's continue here. We'll see this programming demo shortly. So this is one more example. So here, so with GANs, we can do all sorts of funky stuff. One of the things we can do is we can play with image vectors, right? So what is an image? Image is a matrix. It has a set of vectors, right? So I can play with the image vector and create new visual concepts. For example, I take a smiling woman, I subtract a neutral woman, I add a neutral man, I get a smiling man. So I superimpose the style from the woman, the smile, just a smile from the woman on a brooding man's face, right? Here, I took the glasses from the man, put it on the woman, and this is a woman with glasses now. So here I took the smile of a woman, put it on a man's face. In the lower one, I took the glasses from a man's face and put it on a woman's face. Isn't this interesting? So I am playing with image vectors here and I am doing generative modeling. So these images were produced using GANs or generative models. Okay. So basically, what the GAN would be doing internally, it would extract the features of this image, the content features and the style features. It would extract the features of this image. So this is feature vector 1. Okay. Feature vector 1. This is feature vector 2. To extract the smile, I simply have to subtract f1 minus, eventually it's just a mathematical matrix or mathematical vector, as you know, correct? This is my, so this is the smile. This is a smile. I simply subtracted two vectors because the only difference between them was the smile. So I get the smile. I combine the smile with the man's features, which are coming here, feature 3 vector. The feature 3 represents the man's features. So I combine the smile with feature 3 vectors and I get a smiling man, right? Which is very rare in real world, as you know. Mostly it's the women who are smiling, but here we are trying to make a man smile, which is a hard thing to do in real life. Okay, okay, no more jokes. Let me come back. So well, but yes, everybody needs glasses. I can take a man's glasses and put it on a woman. Okay, that's very much possible. Notice something here. The man was wearing regular reading spectacle glasses, but women want to show off and only wear goggles. Alright? Again, leave the joke there. Let me come back here. Alright, let's keep going here. So this is one more example. By the way, the paper where this was provided is also appended below there. So if you were to Google that, you'll be able to find that paper which describes that use case in detail. Alright. So here I'm generating bedroom designs with GANs. The beauty of this is that I can create new interior design, new fashion, right? New interiors, new furniture, new decor, new bed sheets and bed covers and curtains and everything else pretty much. So we as house owners or designers don't have to rack our brain. GAN will give us some cool new design options. It will give us millions of new options. So choosing will become really hard for humans. Yes. Okay. So this was in this paper. It was using something called deep convolutional GANs. Basically, it's using a multi-layer convolutional neural network, both in generator and discriminator. Okay, and it is training a model on 3 million bedroom data set. Then it learned how to produce bedroom designs. Okay, let's continue here. Coming back to our MNIST generator. Now let's see some of this code, how this works internally. All right. Any questions so far? I'll just wait to give you a moment if you want to ask any questions. Okay. Let me continue. So let's look at the code, how this might work. So basically I told you we take noise Z, pass it through my generator neural network, we get an output G. Okay, and then the generator runs one time, whereas the discriminator runs two times. I told you that, right? Notice this generator runs one time, the discriminator runs two times. So the discriminator, the judge, runs once for the generator output, this G. This is supposedly the fake image in the beginning, and then it runs on the real image X. Okay, so X is real image, G is the fake image generated by the generator. Discriminator runs two times. It produces the output value, okay, for the real images is called D real logics, and output value for the fake values, fake images, called D fake logics. It also produces the sigmoid activation of the real logics. D underscore fake is the sigmoid activation of the fake logics. Okay, we produce both the output of the neural network as well as the sigmoid activation output. So key thing here is the generator runs once, the discriminator runs twice, once for real images X, once for generated fake images G. Okay, basically the generator is a two-layer fully connected network. Discriminator is just two layers, FC1 and logics layer. Okay, they are basic neural networks, nothing remarkable. Let's continue. So here it's important to understand what we are doing here. So what we do now, this is the generator loss. Remember, the generator runs once. What is the loss it's minimizing? It's minimizing the cross entropy loss. Okay, the loss between y and y dash. As you know, in either mean square loss or cross entropy loss minimization, I compare it with a known y, the predicted y dash, and a known y. So I compare how far they are, the real y with the predicted y dash. Here, the predicted y dash is 1. So the real. So I'm trying to output, this is my y, 1. It's just a matrix of 1. This is y dash. Okay. So I'm trying to compare the the discriminator logits, which is my prediction, with real ones. Okay. So I'm trying to bring the prediction closer to 1. Basically, I'm trying to bring prediction closer to 1. Idea is the generator has to produce 1, whereas discriminator is comparing the real logics with ones. Okay, so he's saying, okay, well, the real ones should be ones, but the fake ones should be 0. You notice this thing? The real ones should be ones, real images should be 1, but the fake images should be 0. This is key difference. Notice this thing here, ones, zeros. Okay, what we are saying here is the real images should be compared with 1, the fake images should be compared with 0. So I am trying to minimize two losses here, cross entropy loss between this one and this one, and this one and this one. Okay, so I have got two losses to deal with here because the discriminator runs two times. The total discriminator loss is nothing but a summation of the two losses, one loss for the real images, the other loss for the fake images. The real images are being compared with 1, the fake images are being compared with 0. That's what is happening here. Okay, and the generator is trying to compare the output it produces with 1. The generator is trying to give 1 as output. Okay, and the discriminator is saying, well, what comes here is a 0, not a 1. This is the real one which comes from real images. Okay, so it compares these with this, but it compares this value with 0. Okay, so here the real logits are compared with ones, the fake logits are compared with zeros. And then it sends this reverse feedback signal. Well, you send me zeros. So the generator tries again. Okay, so that's what happens. It keeps trying again and again till it produces ones and not zeros. I hope this is clear. Let me continue here. So when I use a fully connected GANs, both in discriminator generator, the generator starts producing more and more realistic character images. Now the discriminator and generator run in an alternating mode, okay? So we can run 10,000 iterations of this entire loop. So first discriminator runs, generator runs, then discriminator runs, then generator runs, discriminator runs. So they run in alternating mode, right? Like alternating current. Well, not a good analogy there. So we can run 100,000 iterations of this entire loop to allow the generator to run to produce realistic characters. For our toy program, which we'll demo here, we'll only run 10,000 steps. After every 500 steps, we will draw a sample from the values run by the generator and print it out. So after every 500 training iterations or training epochs, we will just plot the output produced by the generator and see if it looks like real images yet visually or not. Okay, let's continue here. So this is showing that output. So you could run this with DC GAN or deep convolutional GAN. So here both neural networks. So previous one we did with ANN. This one we are doing with CNN. CNNs help GANs perform better. Notice after training fourth epoch, which is this images, starts looking like real handwritten characters. Okay. In fully connected there, it was not looking accurate even after many epochs. With deep convolutional GAN, it is beginning to look like real handwritten characters much sooner in the process. Okay, so DC GANs are more accurate. They get to accurate generation faster. Okay, let's continue. So one more application is artistic style transfer. Okay, so I could take the content features of this image, the style features from this image, and this is what we get. This is highly creative. You can see the buildings here. You can see this kind of sunny sky and some windstorm. So I superimpose the sunny sky and the windstorm on the buildings and it looks like this. Here I superimpose, you know, this on the same building. So this is my source image and I'm using source this only. So I superimpose this style, I get these buildings in blue hue. I superimpose this style, I get these buildings in red hue. Correct? I superimpose this style, I get these buildings in this kind of a blurry view, and then I superimpose this style and this building becomes this image. So it's the same input image being superimposed with multiple styles. If I superimpose this style, I get this. If I superimpose this style, I get this, and so on. Okay. Finally, when I superimpose this very kind of mixed, complex colored style, I get a very complex, not a very legible building image. I mean, if you see carefully, there are buildings here, by the way. If you were to see very carefully, there are buildings with doors and windows and so on. Okay, but it's becoming very haphazard because the styles input was very haphazard. This is called artistic style transfer, also called neural style transfer. Okay, is this clear? All right, let's continue here. This is done using GANs, by the way. Any questions so far? All right, let's continue here. So this is one more advanced application of GANs. So this is available in this paper again, and here I am doing user based user edit based image search. So let's say this user goes to an Amazon.com website, okay, and they want to find some images of products of this style. So this user starts drawing this. So he uses a marker to draw this triangle, and then this user uses a color pastel to create this on top of this and put a green in front of it. Basically, then our model generates images which match the user edits. Okay, do you notice that? So here is just a triangle. Here is a triangle and there is a element of a blue sky, right? Then there is also grass because there was a green drawing in front of it. Okay, so this is image search based on user edits. So in future, Amazon could provide a color, palette and a marker on Amazon.com website, and I could mark as a user the shape of a phone or shape of a bag, and it will go and find pictures of products which match the desired shape. Let's say I want a triangular smartphone. So Amazon will use my triangular, smartphone edit to try to find phones which match, you know, which match the triangular shape which I have drawn, right? So even search of images or products will become far more sophisticated over time. In the lower one, you can see I'm feeding a query image, and then it finds nearest neighbor photos which match the query image. Okay, so this is image-based search. We call it interactive image generation. Okay, this is image-based search. We call it interactive image generation. So I can do it based on an input image, or I can do it using user edits. So in this case, I'm in this case, uh, you know, it is basically image-based search or user edit-based search, right? So future e-commerce might resort to applications like this, right? I want to find certain handbags. Let's say I start drawing a shoe design. Let's say some lady, she wants certain dress style. So this lady will say, well, I want this kind of dress style, right? And it's using a color palette. She will also color this yellow, this green, right? So using this image, my Amazon server will find images which match this. It will actually generate designs which match this. Okay. So I could do user generated content, UGC. So Amazon could get this new fashion design generated by the user and ask its clothing partners to actually produce this kind of new colored outfit. Okay, let's continue. So one more type of GAN is a conditional adversarial network. Here, both generator and discriminator are conditioned on some additional information Y. So you can see I'm feeding this additional information as a suggestive content. I'm combining it with noise. So this now gets fed to both discriminator and generator. So I am using augmented content Y and giving it a feed and telling it to use Y also in generative modeling. For example, Y could be a yellow bag, right? So I'm saying, well, always have some element of yellow in your bag design, right? It could be a green dress for the lady. So you're saying, well, produce dresses for ladies, but they should be kind of greenish, right? So I could I could suggest by feeding this augmented information called Y here. Y could be any other kind of extra information such as class label or data from other modalities. Okay, and Y is fed to both generator and discriminator as additional input layer. This is called a conditional GAN because now it is conditioned on this new data modality which we refer to as Y. Okay, this is also available in this paper, this entire discussion and algorithm. In future sessions, we'll probably get to deep dive into some of these papers and present the inside story of some of these papers. Okay, so this is an introductory session on GANs today. So one more very popular GAN algorithm is image to image translation. So you can see here I'm giving a suggestion. This is a segmented image if you know your image segmentation, and it is able to produce road conditions similar to that image. I give it this kind of input image, it is able to produce a building design similar to that. And here I am giving black and white and converting to color. So I'm adding color to black and white. This is the input image becoming output. So this is pix to pix translation. There is a certain algorithm called pix to pix transformation. This is what this is doing, and I can convert. This is a satellite photo of this high level view, and it is converting into a geographic land map, right? And here I am taking day, converting to night. Here I am taking a shape of a bag and creating a final colored product bag. This is called image to image or pix to pix translation. Okay, so you can give an input image, it will produce an output image. Generator contains what layers and discriminator contains what layers. This traditional neural network. I'll show you the code shortly. So in both of them are traditional neural networks. Okay, no difference. It's just like two-layered neural network. That's it. Okay, so that was our theoretical part of our webinar today. Our next advanced AI webinar is coming up on RNN. You are welcome to check it out. Okay. All right. Let me now go to some code demo that will really give some more meaning to this whole discussion. So I'm showing you. So we are going to walk through this code slowly so that you can try to understand it. Okay. So I'll go through the main. So basically, it's just developing two neural networks, nothing remarkable. Usual TensorFlow placeholders, right? So here I am just reading the MNIST dataset, right, from the disk, right? So usual placeholders, but the key code starts here. So I am calling a generator neural network, which is a traditional, fully connected neural network, and I am passing initially the noise here. Okay, so it produces output G. This is a fake image generated by the generator. The discriminator runs two times, once on the real image X, the second time on the generated image, the fake image G. Notice this G is being used here. Generator produced fake image G, which is being now fed into discriminator, the judge. And of course, the discriminator is also running on the real images X. So it produces two outputs, one for the real image, one for the fake image. Okay, so the discriminator runs two times, the generator runs only one time. Okay, you see that here. Okay, these are the summary operations for tensor board serialization. I'll skip that. Now here the key thing is, we already saw that in the slide, that for the discriminator loss, this is the scope of the discriminator loss. I have two losses, one loss for the real images, one loss for the fake images. For real images, I am comparing the output with 1. For fake images, I am comparing the output with 0. So I am trying to bring fake images to 0 in the discriminator or the judge, and the real images to 1. So I'm training the discriminator in such a way that it brings the fake images to 0 and real images to 1s, right? So this is 1s like means a matrix of 1s, 0s like means a matrix of 0s. So I'm trying to bring fake images to 0s and real images to 1s. Then I add both the losses, the two losses of the discriminator, to get the total discriminator loss. And when I'm in the scope of generator loss, I'm trying to bring the take logits produced by the reverse feedback loop of the discriminator and produce ones. So I am trying to, the generator is trying to produce ones. Okay, the generator is trying to produce, is comparing what it produces, the predictive output of the generator. It tries to bring them closer to 1. So generator is trying to produce 1. Discriminator is always trying to mark those generated ones as zeros. Okay. And here I am minimizing the generator loss. So discriminator has 2 losses, generator has 1 loss. But in discriminator, I do add the 2 losses. Okay. And this is just extracting the trainable variables, keeping the train. So these are parameters of the model. So for the discriminator model and for the generator model. Okay. Then I minimize the discriminator loss here, right? And the generator loss here. So I'm using Adam optimizer to minimize both discriminator loss and generator loss. Okay. The rest of it is usual neural network computation. So this is where the session actually runs. Instead of 100,000 epochs, I only ran 10,000 epochs so that my model will run on my laptop. It won't take forever. I do mini batch learning. I get the batch size, next batch. I call session.run, right? And then it runs both the neural networks, minimizes the loss. For every 500 iterations, I am printing the output of the generator. Okay. For every 500 iterations, I am printing the output of the, I am plotting the output of the generator. And then I do session.run on discriminator loss and session.run on the generator loss. Okay. And if you see the formation of the 2 neural networks, this is the discriminator neural network. It is nothing but a 2-layer neural network, which you can see here. It's a traditional artificial neural network fully connected. It's not even CNN. Okay. So it's a 2-layer neural network, nothing extraordinary. This is the ReLU activation layer. There is a sigmoid output, right? So I result both the logics, which is the output of the ReLU layer, as well as the sigmoid probability of the logics. The generator is also a 2-layer fully neural network, followed by a ReLU layer and a sigmoid activation. Okay. In that sense, this file does not have anything remarkably new. We are merely defining 2-layer neural network for discriminator, 2-layer neural network for the generator. And this is where I get those neural networks. So when I call this function, and this function is defined in this model.fc file. You see that? So discriminator function, the generator function. This is what I am invoking from the main file. Generator function, discriminator function. Basically, these are the 2 neural network functions. Okay, pretty straightforward. Combined loss minimization of generator discriminator, and eventually the generator, the forger wins, start producing real images or starts producing ones. Okay. Any questions on this code? This is MNIST data generator. Let me show you the output of this. It will take few hours to run this, but I already ran it, so I have the output to show you. So I ran, you know, 20 sets of epochs, and you can see that using fully connected layer, it's going to more and more accurate. So this is the 20th set of epochs, 20th set of training iterations. It started producing nearly accurate handwritten numerical digits. You see that? Okay. But initially it was producing noise. But as it gets deeper into the training epoch, starts producing more and more authentic handwritten numerical digits. I hope this is clear. Any question? How comparison happening between real and fake images? It is pixel-wise comparison. No. I'm not not comparing, I'm not doing cosine similarity or any similarity logic between fake and real images. I am not. I am just comparing the fake images with zeros. Okay. So I'm actually not doing image comparison here. So if I were to compare images, I would compare using cosine similarity. I'm not doing that here. There could be a potential solution, by the way. You could research that and write a paper on it. That what if I were to compare real with cosine similarity? That could be one more solution, yes. But here I have a different technique. I am I'm running discriminator two times. I'm not mixing up the images everywhere. They are not being mixed up. They are not being compared really. This fake image is being compared with zero here, the output level 0. The real image is being compared with output level 1. This is what is happening. And this result, the logic is sent to generator. The generator is trying to output 1. Initially it outputs 0, fake. But eventually, because of loss minimization, so here I am comparing the output with 1. Okay. Here I am comparing output with 1. So here I am comparing output with 0. So there are two different runs of discriminator. There is no mixing of fake and real images happening. So I'm not doing cosine similarity or similarity check between the images. I'm running two different loss functions. Okay. As a whole, I'm combining the two losses and minimizing the integrated loss. Okay. Any other questions? Is the noise input constant every time? In that case, once it is fully trained, there can be only one output from the GAN. How to generate more with the same model? Change the data set for discriminator. So initially it starts with noise, right? It does start with noise initially. Okay. Let's see the code for this. So as you can see, it does start with noise. Yes. Okay. It does start with noise initially. But there is a reverse feedback loop. Okay. So I'm just looking for the reverse feedback loop from the discriminator to the generator. Yeah. Yeah, here is the reverse feedback loop if you see. It initially starts with noise, but this defake logic was produced by this one. For G, the discriminator produces the output of the ReLU layer, which is this, and the sorry, this is the sigmoid of that, and the logic. So this is the output of the ReLU layer. So this defake logic is sent as reverse feedback loop back to. So this defake logic is sent back to the generator. Okay, so the defake for the G sent back to the generator, I call this a reverse feedback loop, and the code which this is here. So during the loss comparison function, you can see the defake logics. So I'm in the generator loss scope. Okay, so this is the generator, the criminal. It is getting the discriminator fake logics from the previous run of the discriminator. So I told you, because it alternates the current. It executes the generator, then the discriminator, then again the generator, and vice versa. Okay, so it keeps toggling between executing the discriminator and the generator. So the the fake defect logic produced by the discriminator will get compared with the generator. During the generator loss, they get compared with ones. Okay, so there is a reverse feedback loop not shown in this diagram. The defect logics are sent here, and this guy, he tries to compare with this with 1. Okay, so here the discriminator is trying to compare this with 0, this with 1, and this defect logic gets sent here. The generator is trying to compare this with 1. Initially it starts with random noise, but later on it compares this. So there's a feedback coming from here, and it gets compared with 1, so that it can output a 1. Initially it outputs 0, but eventually starts outputting 1. Okay, I hope this is clear. Please show input to Z. Okay, so what is Z? Z is nothing but random noise. You see this? Z is nothing, it's random noise. There is nothing more getting filled up in that. Z is random noise. Okay, just a matrix of noise matrix, nothing else. So initially it starts with Z, but later on, during the loss comparison, it is comparing the output of the discriminator, the reverse feedback loop, as I am calling it, the deepfake logics. And you clearly see that here. Okay, so you see that the deepfake logics is fed in the generator logic. Okay, and once. So I showed here, deepfake gets compared. Okay. Yes, the generator will create a discriminated data set. That is the only output possible, because the feedback would be same every time henceforth. See, by the time the generator runs to create data similar to discriminator, both the losses are minimized. My model training will stop automatically, correct? I showed you the loss function curve, which is a convex curve. So I will hit the minimum loss point for generator discriminator, and my training will automatically stop. That's when the weights will stop adjusting because the loss has been minimized. Right? That's natural neural network functioning. I don't have to do anything explicitly for that. Any other questions on this code? Okay, so let me show you once more small program, then we can open for further questions. So here I am going to show you. So I'm taking this bird, I extract the content features of this bird, combine with the style features of this image. Okay, input one, input image number 2. So I want to superimpose this style on this bird. So what I do, I extract content features from this image and style features from this image, because you know each image has features, right? CNNs are very good at feature discovery. Even ANNs can discover features, but CNNs are more specialist for image feature generation or detection. So I'll take content features from this, style features from this, and it is able to produce this output. Okay, this is called creative style transfer, neural style transfer, or artistic style transfer. Okay, so very useful for producing new kinds of art by mixing and matching the style from one image with the content of another image. Okay, so I could produce new fashion design, new interior design, and all that using this. And I can superimpose style from building number 1 onto building number 2. I could superimpose, any film stars, face, and take their film star's face features and combine with an ordinary person's face and create a new kind of star, right? All kind of possibilities exist. Let me show you the code for it. Slightly complicated, but basically I'm using Keras and I'm using a pre-trained VGG16 model. As you know, VGG16 has labeled images. So I'll show you in a summary way. I'm going to concatenate the content image and the style image, and this is my combination image. Okay, in this case, which is generated discriminator, just hold on. So I am concatenating the content image and the style image to get a combination image, right? So that's just a placeholder really so far. So input tensor has 3 images as a placeholder: content image, style image, and the final combination image, right? And then I am taking a pre-trained model VGG16, okay, using ImageNet weights. These are popular pre-trained models on the internet. And on from this, I'm extracting layers. Okay, I'm extracting layers from the block 2 convolutional 2 from one of the blocks of this VGG16. I'm extracting one of the layers. Okay, and I'm extracting. I'm creating a placeholder for content image features and combination feature. All right, sorry. And then I'm saying I'm I'm going to weight the content part. So I'm saying I'm comparing the content image features with the combination feature image. So see, I'm dealing with two images. For one, I'm focusing on content features. For the second image, I am dealing with style features. Finally, there is a combination features. Okay, combining the two. So I'm taking a difference of the content image features, the combination features, weighting them with a content weight, and this is the loss for the content image. Okay, then this is I'm calculating the style loss compared to the style image in the combination image. Okay, in very simple terms, I have three images. Okay, I have three images. This is my content image. This is my style image. This is my combination image. Okay, I'm showing you in a very simple way. I am comparing content feature of these two images. This is my loss for content features. I am comparing the style features between these two images. This is the loss for style image. Okay, you see, so there is a content image, there is a style image, there is a combination image. Combination I create by adding the two vectors, right? The content image vector and the style image vector. Then the difference between content image features and combination image features represents the loss of the content image, and the difference between the style image and combination image represents the loss of the style image. All right, so I will do combined loss minimization again, LC and LS, correct? So by doing combined loss minimization, my combination image will start approaching where it has the content features from this image and the style features from this image. Isn't this wonderful? So when I try to bring combination image both to closer to content image features of content image and style features of the style image, the combination image feature, the combination image, the third one, this one, starts approaching the content of the content image and style of the style image, because I'm comparing with the respective feature set from the two input images. Okay, very interesting logic. And then this is the style loss. I'm comparing style loss is the difference between style features of the style image and the combination image features, right? And again, I'm weighting them with a style weight. I'm also applying something called variation loss across height and width. Okay, so if this is an image, I'm also comparing loss on this axis, loss on this axis. Okay, I'm calling it variation loss, and I'm also adding that to the total loss. Okay, so this is one more loss I'm adding to the whole equation. This needs to be minimized. So I'm adding the weighted variation loss, which is the variation loss across the length and breadth of the image to the total loss. Okay. Then it is usual neural network coding. I take gradients. What is gradient? dj over d theta, correct? I take the gradients of the loss with respect to the combination image, correct? So what is gradient? Gradient is dj over d theta. So this j represents the loss and theta represents the weight vector of the combination image, right? So I take the gradient of that. This is grads, right? Then this is just the loss. I evaluate loss and gradient. So in loss minimization what we do. This is J, which is loss. These are parameters theta, and the gradient simply refers to dj over d theta, as you know, correct? And this is the point where dj over d theta becomes 0 or minimized. So my weight adjustment equation looks like theta is equal to theta minus learning rate alpha dj over d theta, the gradient as we call it. Correct? This is my weight adjustment logic, as you know. Correct? dj over d theta. This is my gradient. So I multiply with the learning rate, and this is my weight adjustment equation. Okay. So I am calculating J, which is loss here. Okay. This J is the loss and gradient. Okay. And gradient is dj over d theta, and loss is the loss J. Okay. That's all I'm calculating here, evaluating. Then I run one algorithm called fmin1bfgs. There is an algorithm called LBFGSB. It's a loss minimization algorithm. Okay, it's available in the SciPy library. It's a loss minimization algorithm. Many of our optimizers and scikit-learn TensorFlow also use this for loss minimization. And then I minimize this loss and with respect to these gradients. Okay, I minimize the loss with respect to the gradients. That's pretty much it. I run so many iterations and my model trains and the loss is minimized with respect to the gradients. And at the end of it, what has now happened that they were to draw three images again. This was my content image, this was my style image, this was a combo, right? Combo, combination image. So I brought the content features close to the content features of the content image. I brought the style features close to the style features of the style image. Ultimately, the combo image has content features from the content image and style features from the style image, right? So now I have a style transfer which has happened. The resultant image has content from image number 1 and style features from image number 2, because I am trying to minimize the loss here and the loss here. I am comparing C with combo and S with combo. Okay, that was the loss, the comparison, the minus sign. Okay, we saw that here. In case you missed it, we saw that here, right? We saw that here. We were taking a minus sign of content image features with combination features, weighting it with content weight, adding it to total loss. And here we were taking style loss and style loss. So we are comparing style features with combination image features and weighting it with style weight and adding it to the total loss. Correct? So I do total loss minimization. I do add something additional here called total variation loss, which is variation across height and width of the image. I add that to the overall loss, weighted variation weight, and then I get the gradients. Okay, and I just run gradient loss minimization with respect to the gradients using this loss minimization algorithm called LBFGSB. Okay, it's a very popular loss minimization algorithm and it's available under SciPy library in Python. So here I am using different Keras capability. Okay, I'm using Keras, I'm not using TensorFlow here. If you see, TensorFlow was never imported. I was using, it's a completely Keras based program. But now, as you know, Keras is also available as part of a package within TensorFlow, right? This is an independent Keras program. And I'm using the loss minimizer from SciPy library called BFGSB. Okay, no TensorFlow here, raw Keras code along with some help from SciPy code. Alright, I hope you understand this program as well. This is slightly more complicated. I am open to any questions now. You have any questions for today? I suggest you try some projects. You know, if you try some project, there are so many research papers that demonstrated and on a high level. So you pick up a project and use Google Colab or AWS server and try out some of these. The GitHub code is often provided along with the paper in Google and find a lot of these GAN use cases. Try to run it in Google Colab or TensorFlow and or AWS server and just experience it for yourself. Okay, that's the best way to learn this thing by running these models on your own. Would we get this code? Okay. Normally we don't provide the code we have, but some of our lab members do share the code. We can talk offline on this. Kindly reach out to me offline. Our course students get the codes, right? Folks who have registered for our courses, they get lots of projects from us. Any other questions? By the way, let me tell you, a lot of this code can be found by Googling it. Okay, so I also got it from some GitHub of somebody. It's not like we wrote this code from scratch. We might have tweaked it, but a lot of this code was available on different GitHub libraries. Okay, by Googling, you can find it. Any other questions for today? Okay, going once, going twice. Any final questions? Our future sessions include one is an RNN overview, and there is one more coming up on reinforcement learning, where we'll introduce the concept of reinforcement learning and create a focus group for reinforcement learning within our AI research lab. Okay, so we want to get into emerging areas like reinforcement learning, driverless cars, advanced computer vision, advanced NLP, and so on in our AI research lab. All right. In this case, which is discriminator and generator? I'm not sure what this question. I think we answered before. For the last one, for the last one, well, there wasn't a clearly defined generator and discriminator. So it was style transfer using Keras and SciPy code, and it was not a traditional GAN design in that sense. We didn't see two neural networks. We were doing slightly lower level coding using Keras for showing demonstrating style transfer. So we didn't really build out two neural networks per se. So it's a relevant and good question. In the last examples I showed you for style transfer using Keras code, we did not see two neural networks. It was simply raw Keras code with SciPy. Okay, there wasn't a dueling neural network shown in that code. We did style transfer using Keras code without neural networks. Any other questions? Okay, I thank you for your time. I'll see you in our next session. Have a good day.